Hello everyone, this is Professor DePaulo. Welcome you back to Psych 220 Behavioral Statistics. More lab. And today I'm going to walk through how to complete the lab practice step by step. And the lab practice is going to be the key to the lab final, obviously. And it's open book, open notes, open video. If you're going to use videos, please bring headphones or earphones of some kind so that it's quiet and you don't disturb other people, but you are allowed to watch whatever videos you want to watch, including this one. So what I'm going to do here is go step by step, problem by problem, and show you how to report the data as well. I'll open up a Word file just so that we can look at how to report the data, report the results also. So let's start with number one. So we have this data set, and I've uploaded the practice lab data set. And this over on top of it, so you don't have to type in anything. It's already there, practice lab, at practicelab.sav file. And this is the legend. Basically, this tells you what the variables are. Depression scores before CBT. CBT is cognitive behavioral therapy. So what is the depression level before cognitive behavioral therapy from 0 to 100? Depressed 2, what is your depression after? So this is a before-after variable. Before cognitive behavioral therapy, after cognitive behavioral therapy. Gender, 1 male, 2 female, just to simplify things. Married, 0 not married, 1 married. Stress, self-reported stress level, right? So far, depression 1 is continuous, depression 2 is continuous. Gender is discrete, it's a nominal variable, categorical variable. Married is also categorical or nominal variable. Stress is a continuous variable. School is also a nominal or categorical variable. Level of education, 1 high school, 2 some college, 3 some college degree, 4 master's degrees, 5 PhD. Income, annual salary in thousands, this is continuous. Medication, receive medication for depression, this is categorical or nominal. 0 no, 1 yes. Only 2 groups here. See how school has multiple groups? Medication, only 2 groups. Gender, only 2 groups. Married, only 2 groups. That plays a role in your analysis. And then drug, only 2 groups. Categorical again. Uses drugs or does not use drugs. So those are the description of the variables. I've only given 25. So what I did was I took a data set with this information in it, and I cut it down to 24 or 25 cases, just so that you're not burdened with doing, several hundred cases at once. And so I put the cases in an Excel sheet, and I put it on the sheet originally because I had people type in the data. But afterwards, I just made an SAV file for this, so you don't have to type anything in. Typing data into Excel is a skill that you would want to have. Maybe not for this class per se, but moving forward, in case you get a job and you need to use Excel. So like when I got a job as a data analyst, whatever they called me, for an insurance company, I did tons of stuff in Excel because they were more interested in Excel at that point than they were interested in SPSS, SAS, R, things like that. They wanted graphs in Excel, tables in Excel, because they knew what that was. They were used to using it at the corporate level. So it is important to be able to enter data into Excel. The first row is always the variable names, and then you list in the second and subsequent rows what the data is. And then you could just import it directly into SPSS or R, or wherever else you want to use want to do your data analysis. So it's really good for formatting data. It's not good for analyzing data, Excel. But it is a tool that you should have because so many people are qualified. You need every advantage when you're going for a job that you can get. Okay, so that's kind of the rationale behind this. But I've made the SPSS file for you to save you time. Question 1, provide the means and standard deviations for depression, stress, and income. This is how I would do that. So here's my data in Oporto, right? So we're going to look at depression 1, stress and income, means and standard deviations. This is the easiest way that I would do that. Analyze, descriptive, descriptive. Now there's multiple ways to do this. You could do this in Explorer. You could do this in descriptives. There's some other menus that will get you what you need here. But this is a way to do two problems at once. So analyze, descriptive, descriptive. And we're going to look at depression. We're going to look at stress and income. Under options, make sure you have mean and standard deviation. I will uncheck everything else. Leave this the same. Just have mean and standard deviation. Continue. Check this box here because this is going to make the z-scores. And you're going to need the z-scores for a later question. I think it's question 2 or question 3 where you're going to have to look for outliers. And to look for outliers, we're going to use z-scores. So make sure you check this box so you make the z-scores and you get 2 questions done basically at once. Hit OK. Here's our means for depression, standard deviation, stress, and income. So you're just going to copy these onto the sheet. For problem 1, copy it here. And then see problem 2, where it's talking about outliers here. You're going to be able to look at the z-scores for the outliers. So we're going to get to that shortly. So problem 1 is done. Analyze, descriptive, descriptive. Problem 2, create histograms for each of the variables in question 1. Indicate the shape and then the outliers, which we already have the z-scores for. So histogram and shape. So to do histogram easier, analyze, descriptive. I prefer to do explore here to get the histograms all done at once. So we want depression 1, stress, and income. In the dependent list, don't put anything in the between subjects or factor list because we're not looking at the histogram for a particular level of a nominal variable here. We don't need that. If you just want the histogram, you hit plots. If you want the statistics and the histograms, you're going to hit both. I'm just going to hit plots here so I don't, come up with a bunch of other stuff that I don't need. Under plots, get rid of box plot. We're not looking at that. Hit none. Get rid of stem and leaf and just check off histogram. So none, histogram, leave this blank. We're just going to look at the histogram because it's the easiest one to use. Continue and then OK. Here's our histograms. So depression, you see how it comes up and the tail's to the left? So tail to the left is negatively skewed. Stress, once again, tail to the left. These graphs are not going to be perfect. So you have to pick the best description of the shape. It's not like perfectly generated because it's actual data. Actual data is not as nice as the data I make up, say, for your exams, where I try to make them where the calculations are much easier or as easy as possible. Actual data is messy, so you're not going to get a perfect situation, but you're going to get tail to the left here. You're going to get tail to the left here, right? And then histogram here for income is tail to the right. These are not bimodal because this is only basically one case. So this is an outlier to the right, which creates the skew, positive skew here. You have this here, but this is not bimodal because you don't have like a cluster of multiple bars here. And you have an easily tail to the left here. And just do your best to identify the shape. Some of them are like in between, but most of these I would classify as mainly negative skew, positive skew. If you have trouble with looking at the graphs, you can go back to Analyze, Descriptive, Explore, and you can look at the statistics of the plot. Just leave it like this. Options, leave it alone. And this will give you some skewness information. So you see skew, it's a negative value. The bigger the negative value, the more skewed it is. But it's a negative value, so it's negatively skewed. Stress, negative value, negatively skewed. Income, skewness is 2.4, so positively. This is a big skew here. So the greater the number, the greater the skew, basically. So that gives you a verification about skewness from the data. If you want that, you don't need it. You can just look at the histogram. Okay, outliers. Number 2 still. So we're calling outliers anything greater than or less than 2.58 for a z-score. The easiest way to do this is to go to the data. Let me close this for now. Go to the data and just manually look at this. Scroll and find 2.58 and then find the case number. Here's case number 17. 17 is the row here. That's the case number. 17 is an outlier for depression because negative 2.7 is greater than negative 2.58. And that's the only outlier here. For stress, we're looking for 2.58 and negative 2.58. Same thing, case 17. There's another outlier. And then for income, 2.58, we go down here to case 24. So that's by far the easiest way. There's not a lot of data here. You can just eyeball it. If you don't want to eyeball it, you can do select cases and do the conditional, right? So data, select cases, and then do if, and we're going to look for depression. So we're going to look at the z-score. Actually, we need the z-score for depression. We don't need just depression. We need z-depression. We're looking at the z-score. Is it less than or equal to negative 2.58? Or is this vertical line is or the z-score is greater than or equal to positive 2.58. So I'm looking at the extreme tails here. And it's going to only select cases that are meeting these either of these criteria because it's or. So either the z-score is less than negative 2.58 or equal to negative 2.58, or it's greater than or equal to positive 2.58. When I do that, look what happens. All the cases get crossed out except for row 17, showing that 17 is the outlier on depression, z-depressed one. If I had a huge data set and I didn't want to look at the row, I could do analyze, reports, case summaries, and I could look at z-depressed one, right? And I would look at the case numbers here, and it would show me the one case that's selected, and this is the z-score. So only one case is the outlier. So if I had a huge data set and I didn't want to scroll through the rows, I could do analyze, reports, case summaries after I've done the select cases, and put pretty much either depression or you can put even depressed one here. I put the z-score in here, it's fine. Display cases, show valid cases, show case numbers, and it'll give you the case number. But with such a small number of cases, you can just eyeball it. It's just faster. If you had a huge amount of cases, I would do it the second method where I do the select cases and then I do the case report, case summaries. You can sort it, but sorting it can screw up the case number. So I would try not to sort from high to low. I'm a little worried about sorting things that you won't get the right case number that way. All right, so once you're done, if you do select cases, you need to get rid of the filter. You always have to get rid of the filter before you do the next problem, or you're going to have a screwed up data set. You're going to have a data set of one person. So clear this filter. My whole data set is now selected. It's all open. And we can move on to the next one. Number 3, provide the correlations between depression 1 stress and income, and depression 1 and income. I can throw them all together into one one operation here in SPSS. So analyze, correlate, bivariate, because we're doing 2 variables at a time. Bivariate means 2. Depression 1 here, stress here, income here. Check off Pearson. Make sure two-tailed is checked. And I prefer to check these 3 at the bottom here. Diagonal, show lower triangle, and flag significant correlations. And then hit OK. And these are our correlations. So you make sure you look at Pearson, the line that says Pearson correlation. Right? So any asterisk next to the correlation means it's significant. That means it's significantly greater than 0. The correlation is not 0. You see that there's no asterisk here by any of these. So it's telling you that they're all not significant. Depression 1 and stress, just find the intersection here between these two. 2.64, not significant. You see the p-value, the sig value is 0.202. That's not less than 0.05, so it's not significant. But if you put the asterisk box here, it'll give you an asterisk when it is significant. So it's easy to visualize that. Depression and income, negative 0.102. That's also not significant. And stress and income, negative 0.038. That's also not significant. So your correlations are 0.264, negative 0.102, and negative 0.038, and they're all not significant. They're all pretty weak correlations. Let's go back here. So that is number 3. Number 4, does stress significantly predict depression 1? So this is regression because we're asking about prediction. Whenever you see predict, it's regression, linear regression. So stress is the independent variable, it's the x. Depression is the dependent variable, it's the y. So we're going to do this. Analyze, regression, linear. We want depression as our dependent. We want stress as our independent because that's the predictor. Okay, then hit OK. What we are seeing here is the model, the regression model. The R squared is the variance explained. All right, so that's a question right here where it says, what percent of variance does stress account for? Well, if we want to make this into a percentage, multiplied by 100, it's going to be 7%. So this model is only accounting for 7% of the variance in depression. So stress only accounts for 7% of the variance in depression, which is not a lot. That means there's 93% of the variance unexplained. Is this model even significant? That means, is it different than 0? So in the population, is this model different than 0? Does it predict more than 0% of the variance? And here's the significance test. It's the ANOVA. You look at the F, and you look at SIG. So is this significant? The answer would be no, right? This is number 4. Not significant. And then I like to give the F value here. I prefer to give the degrees of freedom. You don't have to. You can just give me the F value, 1.726. And then the significance value is P, 0.202. So that is not significant. It's not significantly greater than 0, which means it's a really terrible model. Which basically means that stress is not a very good predictor of depression. So that's how I would write the answer, not significant. You cannot just write yes or no. You need to give me evidence that shows that you understand what you're looking at. Because yes and no, it can just be guessed. This tells me you know what you're looking at the ANOVA here to test the significance, and you're writing the significance out. This is the F value. This is the degrees of freedom, 1, 23. Here's our F value, and here's our sig. You need to at least give me the F value and the sig. Okay? With the yes or no. So that's how I would write it. What is the equation of the regression line? You got to look at this coefficients box. And if you look at the coefficient box, you get predicted y. I'll put y prime as predicted. You might see y hat. I don't know where the hat symbol is here in Word. So how do I write it? The predicted y is equal to, you want the slope, right? Because it's bx plus a, that format. So we got to put it in that format. B is the slope. Where's the slope? Well, if you look under coefficients and you look under capital beta, where it says unstandardized coefficient, the slope is next to stress. 0.216, that's the slope. 0.216x. I'll put x in parentheses just to separate it. 0.216 times x. And then the y-intercept is where you see constant under the capital B unstandardized coefficient, plus 43.196. That is our regression line. So that is our prediction line based on stress predicting depression. It's not a good model, so there's going to be a lot of error for using this line, but that's the line you would use if you're using the model. Now, the next question is asking about predicting depression for a stress score of 85. You would just plug back into the equation. 85 would go here. So it'd be y prime equals 0.216 times, typed that wrong, 216 times 85 plus 43.196, and that's going to give you the point on the line when x is 85. And you got to plug in, you got to do a simple calculation here. So you break out the calculator or whatever you got to do this. 0.216 times 85 plus 43.196, 61 point, rounded to 2 decimal places, 61.56. And that's your predicted value of depression for a stress score of 85. And then you're done with number 4. Number 5. Do illegal drug users differ from non-drug users? Now, drug users, there's 2 categories, 2 groups. So you know it's a t-test. Because 2 groups and you're looking for the difference, it's a t-test. Are these groups independent? Yes, because you're either a drug user or you're not a drug user. You can't be both. So it's independent and it's a t-test. So it's an independent t-test. So we're going to go and do the independent groups t-tests. Analyze, compare means, analyze, compare means, independent samples t-test. We're going to do drug as our grouping variable. And how is drug coded? It's coded as, let's look at drug, 1 and 0. Where 0 is non-drug and 1 is drug. So it's coded as 1, 0. We got to put that here, define groups. We got to have the 2 values. Doesn't matter what order it's in. And we're looking at income, right? We're looking at annual salary. So we're looking at income. Income is my test variable, the dependent variable. I don't need effect sizes. Homogeneity variance test. I don't like that, so don't check that off. That's Levine's test. Hit OK. Here's our t-test. We see here that non-drug users have a mean of 54, so that's $53,000 a year. Drug users, that drops down to $31,000 a year. So just eyeballing it, it's a gigantic difference. Is it significantly different than zero, though? With a small sample, that's the key. And we're looking for differ. So we're not giving a direction of the effect. We're looking at differ. So we're doing a two-tailed test. We're going to always choose equal variance assumed, right? Because we're assuming that the variances are relatively equal. So we're going to choose equal variance assumed. Top row, 1.929, degrees of freedom 23. So how am I going to write this? Let's first find out, is it significantly different? Two-tailed test, so two-sided p, 0.066. That is not less than 0.05, so that's telling me that drug users and non-drug users are not significantly different in terms of salary. So there's a huge gap here. The problem is that the sample is so small, it's only 25. So this gap is going to be significant for bigger samples. But since we have such a small sample here, we don't have enough power to reject the null here, right? So what ends up happening is we're going to make a type 2 error here. I'm pretty much guaranteeing it because these means are so big, are so different. You're only being constrained by the low sample. So the low power here is creating that type 2 error. If I increase the sample to 100, I can almost guarantee that this is going to be a significant difference. You know, if I were to run the effect size measures, the effect size would be pretty large, which is indicative that the study is severely underpowered because the sample is very small. So the answer here is no, because the two-tailed p is 0.066. So we're going to say not significantly different. T, degrees of freedom, is 23, equals 1.929. P-value, the two-sided p-value, 0.066, not significantly different. And that's your conclusion. You can't just write yes or no. You've got to give me stats to show that you know what you're looking at. Let's look at the next one. Does level of education have an effect on annual salary? Okay, so education, that's our grouping variable. How many levels does it have? Let's look. Level of education. So high school diploma, some college, college degree, master's degree, PhD. So there are 5 categories here, 5 groups. And we're looking at annual salary as our dependent variable. So if I have 5 groups, I can't do t-test because t-test is only 2 groups. So more than 2 groups is always ANOVA. So I'm going to do the one-way ANOVA with education or school as my between groups factor, my independent variable. So let's do that for number 6. Analyze, compare means, one-way ANOVA. School is the variable we're looking at, the factor, right? That's the nominal variable, the grouping variable. I don't need effect size for this. My dependent list is salary, so it's income, right? It's asking for salary. Salary, yeah. And I don't need to do post hoc yet because I want to see if this is significant first. So just leave it like this for now and hit OK. And our one-way ANOVA is significant, 7.375. The p-value is less than 0.001. So that is a significant difference. there is a significant difference for number 6. Our F is 420 between and within, and that's equal to 7.375. And our p-value is less than 0.001, so that's less than 0.05, so it's significant. Once this is significant, we can do post hoc tests. Which levels are not significantly different from each other? So I'm asking you, which levels are not? Well, first off, how many comparisons are we going to make? And we're going to do Tukey test. Well, we have 5 groups, so the number of comparisons five groups, so 5 times 5 minus 1, which is 4. So number of groups times number of groups minus 1 divided by 2. That is the formula, right? So the formula is basically k, where k is the number of groups, times k minus 1, and all of that divided by 2, right? So this whole numerator divided by 2. So here we're going to have 5 times 4, and we're going to divide that by 2. That gives me 20 over 2, which gives me 10. So there are 10 post hoc comparisons. There's 10 Tukey tests we're going to run among our 5 groups. So which ones are different? I mean, which ones are not different? So which ones are the same, basically? So I'm asking here which ones are not significantly different. So be careful how I'm asking this. We're going to run that Tukey test, that ANOVA again, analyze, compare means, one-way ANOVA. We're going to leave this alone, but we're going to do post hoc, and we're going to check off Tukey. Just check off Tukey and hit continue, and hit OK. And now we have our Tukey tests. So wherever you see an asterisk here, that means there's a significant difference. Wherever you don't see an asterisk, that means there's not a significant difference. So we're asking which ones are not significantly different here. So which ones don't have asterisks. And also remember that this is the full matrix, so there's more than 10 here, right? There's 1, 2, 3, 4 times 5. There's 20 rows here. 10 are the comparisons. The other 10 are duplicates, right? So 1 and 2 is the same as 2 and 1. These two are duplicates, so don't look at 1 and 2 as different than 2 and 1. It's still the same comparison, the same values, right? One's with a negative, one's with a positive. Look for the ones without an asterisk and look for the 10 unique ones. So what are the 10 unique comparisons here? 1 and 2, 1 and 3, 1 and 4, 1 and 5. All right, now 2 and 1. So 2 and 1 we have. 2 and 1 is the same as 1 and 2, right? So we're not going to do 2 and 1. We're going to do 2 and 3, 2 and 4, 2 and 5, right? Now for 3, we're going to do 3 and 4, 3 and 5, and for 4, we're going to do 4 and 5. Those are our 10 unique comparisons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Which ones of these are not significantly different? So let's look at 1 and 2. 1 and 2 doesn't have an asterisk, so 1 and 2 are different. So 1 and 2 is different. What else? So 1 and 2 is different. 1 and 2 is the same. We're looking for the same. We're looking for not different. 1 and 2 is the same. 1 and 3 is the same. 1 and 4 is the same. 1 and 5 is different, so we're not going to list that here. All right. 2 and 3 is the same. So we're going to list that here. 2 and 4, it's the same. 2 and 5, it's different because it has an asterisk. I'm not going to list different. 3 and 4 is the same. 3 and 5 is different because there's an asterisk. 4 and 5 is the same. And that's it. So the same, the ones that are not different, 1 and 2, 1 and 3, 1 and 4, 2 and 3, 2 and 4, 3 and 4, 4 and 5. So 7 are not different, only 3 are different. The 3 different ones are 1 and 5 here, 2 and 5 here, 3 and 5. Those are the different ones. Everything else is not different. So that's the Tukey for number 6. Number 7, the average annual income of people in the U.S. is 40. Is the average annual income of the sample different than 40? So we're using a sample and we're comparing it to a mean, a population mean. So one sample compared to a mean is a one sample t-test. Because we obviously don't know sigma. We don't know the population standard deviation. We don't know the mean. So one sample t-test, analyze, compare means, one sample t-tests, and we're comparing income to 40,000. Is income greater than, no, different than 40? So two-tailed test. Let's look at income. Is it different than 40? So put income here. We're testing against 40. So 40 goes in the box. We don't need effect size. Hit OK. Is income different than 40? The answer is two-tailed P, 0.360. So no, income is not different than 40. So that's significantly different. How do you report that? For number 7, not significantly different. T, degrees of freedom is 24, equals 0.934. P is 0.360, not significantly different. For number 7. Number 8, does CBT have an effect on depression? CBT, let's take a look. Well, if I look at the data, there's 2 values for CBT. There's depressed 1, which is depression before CBT, and depressed 2, which is depression after CBT. So this is your classic before and after. There's 2 groups, so it's got to be T. And the 2 groups are related because it's the same people, before CBT and after CBT. So it's going to be paired samples T. So we're going to go into the data here, SPSS, analyze, compare means, paired samples t-test for this. Depression 1, depression 2. Don't need effect size for any of this. Just put depression 1, depression 2, hit OK. Are they different? P-value, two-tailed, 0.035. That's less than 0.05, so there is a significant difference. So there is a significant difference. T is, degrees of freedom is 24, equals 2.231 here. And our p-value two-tailed is 0.035. There is a significant difference in depression after CBTs. And if you look at the means, it goes down. So people started with a 57 score in depression before CBT. After CBT, that depression score drops to 51. But we're just asking for a difference. We're not asking for lowering. We're asking for a significant difference, so two-tailed, and then there is a significant difference. And that is the practice lab. So if you can go through all this and you realize that different questions are based on different labs here. So I've covered all the labs, right? And so each question generally represents a different lab. So a different procedure. There's no real duplicates on the exam. So you have to identify the test. The final lab is going to be very similar to the practice lab. And then you're going to write. You have to indicate. So you're going to have to write on the test whether things are significant and provide the statistics to indicate whether it's significant or not significant. Right? You have to provide the different. You cannot just write yes or no. Okay? So hopefully that helps you. Go through it. Take notes on it. Come prepared. It's open book, open notes, open everything, open video. If you're gonna listen to videos, make sure you're bringing a something like earphones, headphones, whatever that you can plug in and listen to videos. So, but there are no phones though. There are no cell phone usage. So you cannot text each other the answers to the test during the test. You can open everything else, but there's no phones. So if you're going to listen to video, you're going to have to listen to it on the computer and not on your phone. And not on your laptop. Unless there's something wrong with all the computers. You're going to use the computers. Okay, folks. Hopefully that helps. If you have any more questions, let me know. If not, bye for now. See you for the lab final.